Shall we begin? Yeah. So welcome to this symposium, and this time we are talking about principal knowledge in math. So first of all, we have Katherine sharing with us about the development of children's principal knowledge, and then I will talk about the cognitive predictors of different AP understanding. And then Richard and Anna will be sharing about the interventions on this domain. So maybe we can pass the time to Katherine to share about the development of principal knowledge first.
Hopefully that is appearing now. Yes, excellent. Oh, how do you start the slideshow in your, I'm just going to hit this because I couldn't see. There. Is that good? All right. So I'm going to be talking briefly about a longitudinal study that we conducted on children's understanding of inversion, associativity, and equivalence with a study conducted with 2 of my students. And the first thing I want to address is why study conceptual knowledge of arithmetic, especially since I'm going first. What children know and understand about addition, subtraction, multiplication, division, and about the equal sign is considered to be critical for the basic understanding of arithmetic and also the foundation for later mathematical knowledge and skills. And this knowledge of these operations in the equal sign is often referred to as conceptual knowledge. And the other reason to study this is that obviously it's becoming of increased interest to researchers, which is why we have a symposium kindly organized by Terry. There are 3 types of arithmetic problems that I focused on in this study: inversion, associativity, and equivalence. And you can use conceptual knowledge of arithmetic to solve these quickly and more easily than if you don't apply your conceptual understanding of arithmetic. So in inversion, if you understand that addition, subtraction are inversely related, or multiplication, division are inversely related. If you understand that, you know that the answer is just the first number. You don't have to do the math. With associativity, you can make your life a little bit easier if you start with the subtraction or the division. And with equivalence, there's a couple of ways that you can demonstrate your understanding of the equal sign. You can ignore the 2's on both sides and just deal with the 9 and the 7. Or you can do all the math on the left side and then figure out what number needs to be added to the 2 or multiplied by the 2 to get your answer. Now, those problems are really interesting because they're novel for the children in our studies, and so children haven't been taught a procedure to solve these problems, so they can't just apply a rote procedure and not understand why it works. They actually have to use their conceptual knowledge to come up with a conceptually based strategy to solve these problems really efficiently. So that takes us to, well, why should we do a longitudinal design? Well, longitudinal designs allow us to examine groups of individuals across several time points, get more detailed understanding. They are considered to be a positive research design, a good research design that's often useful in developmental psychology, but they've actually been pretty infrequently used in conceptual knowledge of arithmetic. And so I decided to finally bite the bullet and take on a longitudinal study, which is what I'm going to talk about today. Very briefly, and if you have questions, I'm absolutely happy to answer them either during the talk or after the talk, or email me later. But our final sample were 42 participants who, at the beginning of the study, were in grade 4. They were average of 9 years and 6 months at the start. And we talked to them in November and May of grade 4, grade 5, and grade 6. And we asked them to solve inversion and associativity and equivalence problems like the ones that I just showed you. And I have to take full blame responsibility for this. I made an executive decision to use the same order of problems every time. So it is a limitation of the study, but there were reasons for it. Always had additive problems and then multiplicative problems. Just because counterbalancing got too complicated. We know that from previous research that doing additive problems first can actually promote conceptually based strategy use on multiplication problems, and we don't typically find the reverse. So hopefully this actually increased conceptually based strategy use on multiplication problems, but you'll see what happens. The measures that we used were accuracy, but what I'm going to focus on are immediately retrospective verbal reports of their problem-solving strategy. So they solved the problem, told us the answer, and then we said, how did you get that answer? So that's the data I'm going to be talking about. Going right into our results, just to give you an overall view of how frequently conceptually based strategies, making use of knowledge of inversion, associativity, and equivalence were used across the study. What you can see on top are the additive problems, on the bottom are the multiplicative problems. Inversion is in black, associativity is pale gray, equivalence is dark gray. And so I'll just talk about those results very briefly. One of the things that you should be able to see fairly obviously is that conceptually based strategies were used more frequently on additive problems than multiplicative problems, except on equivalence problems, which were equally used. Conceptually based strategies were equally used on equivalence problems, whether they were additive or multiplicative. What we also see is that by the end of grade 6, there's still lots of room for improvement. So the graph actually only goes to 90%, not to 100%. And so what you can see is that even by the end of grade 6, we're hovering at about 70% at the most of conceptually based strategy use. So there's still room for more conceptually based strategy use. So that's our first results slide that I'm going to talk about. The second results slide has to do with when did participants first use a conceptually based strategy on each problem type. And again, you can see on the additive problems that kids actually started using conceptually based strategies pretty early. So often in grade 4, a little bit in grade 5, and then it kind of petered off. Most kids by the end had used conceptually based strategies on additive problems. I'll talk about that more in a second. On multiplicative problems, you can see that equivalence seems to be understood and used right away by about half of the participants, and then gradually a few more start using or showing indications that they understand the equal sign as we move through. So that's another way of looking at the data in a brief way. The last result that I want to talk about is kids who never used conceptually based strategies. And so on additive problems, 7% of kids never used a conceptually based strategy on inversion versus 14% for associativity problems and 0% for equivalence. So every single child ended up showing that they understood the equal sign on additive problems. They used it at least once in the 6 times that we talked to them. Contrast that to multiplicative problems. On multiplicative problems, 33% of kids never used the conceptually based strategies on inversion problems. 62% never used conceptually based strategies on associativity problems, and 20% did not use conceptually based strategies ever on multiplicative problems. So definitely some differences between the problem types and also between additive and multiplicative problems. So this takes me to, is there any good news here? And I think there is. I think I'm more certain about bad news in terms of the study, at least with Canadian children in Saskatchewan, perhaps. Equivalence seems to be quite well understood. Phew. So by grade 4 through 6 seems to be quite well understood. It doesn't seem to be as dependent on operations, which makes sense. It's about the equal sign, not about multiplication or division or addition, subtraction. But it is interesting that it doesn't seem to be as well understood on multiplicative problems, with 20% of kids never actually showing any understanding of equivalence on multiplication problems. So there is still some concern with that, even though overall equivalence seems to be well understood. Additive inversion seems to be well understood. Only 7% of the participants were not showing any signs of understanding inversion by the end of the study. But still, by the end of the study, 70% was the highest that we got in terms of overall inversion conceptually based strategy use. I left this in my slide, the test wiseness problem, but for the sake of time, I'm going to cut that. I just forgot to change my slides. I'm going to get to the bad news, and the bad news is multiplicative inversion was only, didn't even get close to 50% use by the end of the study, which was a bit disappointing. Even though participants seemed to gradually discover the strategy across the study, you know, 1 or 2 students discovered the strategy and applied it as we moved through the 6 sessions. But there were still a third of participants by the end of the study that still had never shown any indication of a conceptually based strategy use on the inversion problems, which actually parallels a study that I conducted with Adam Dubé, who is also here. We did a microgenetic study on multiplication and division, and by the end of that study, a third of participants had still not discovered and applied conceptually based strategies on inversion problems. And then the second thing is, and this is consistent with previous findings from our labs, is that even though associativity, conceptually based strategy use on additive associativity problems was better than on multiplicative problems, it's still pretty weak overall. And there's probably good reasons for that. There's no clear visual pattern on associativity problems like there is with inversion problems. And unlike equivalence problems, you don't need to understand the equal sign to be successful at solving the problems. You can still make do with a left to right strategy on associativity problems and get the answer. So overall, my conclusion is that these results do suggest that, at least for Canadian children, direct instruction might actually be needed to promote conceptual understanding of arithmetic, particularly for multiplicative inversion problems and for both types of associativity problems. And that instruction, I think, is important given how critical the information on how the operations relate to one another and how important understanding the equal sign is for more complex mathematical skills. Thank you.
Thank you, Katherine. So maybe we have time for one questions.
I have a question. If
Sure.
anyone else does. Did you ever see kids who used a strategy, a conceptually based strategy, at one assessment point, then stop using it later? So I'm curious about whether you saw a lot of variability in regressions.
We typically saw that once kids had acquired the strategy, they tended to keep using it from one session to the next. And that was my test wiseness point, was we used the exact same problems all 6 times. And so I was worried that they would know the problems, but no one ever mentioned that I'd solved this problem already, but they did get test wise in the problem type, because these are novel problems they don't see in any other context. So I think they went, oh yeah, these problems. And so I think then they remembered the strategies that they'd used the previous time.
Thank you.
Now maybe I will start my second talk. Can you see my screen? Okay, yeah. So here I'm going to talk about the cognitive predictors of arithmetic principle understanding. So math is a very broad area, so I think there are 3 major elements that we have to consider when we talk about children's math achievement. The first one is numbers, second is arithmetic operations, and the third one is the ability to convert a word problem into a number sentence. So a lot of studies actually focus on the first component, which is the numbers, but the other 2 components are very important. And in this talk, I'm going to focus on the understanding of arithmetic operations. So how do we actually measure that? We can measure children's understanding of arithmetic principles, what we call APs, which are the fundamental laws and regularities within the arithmetic domains. So examples include commutativity, inversion, and relations to operands. So Katherine has talked about inversion, so maybe I will focus on commutativity and relation to operands. So commutativity refers to the order irrelevant principles. So in addition and multiplication, so the order of operand is actually not important. A plus B is always equal to B plus A. And for relation to operand, it basically refers to the relation between the operands and the answers. So for any addition problem, A plus B, as long as the B is a natural number, you always get an answer that is greater than A. Okay, so these are the relations between the operands and the answers. So why are these principles important? There are theoretical reasons. For example, if you understand commutativity principle, the number of arithmetic facts that you have to remember can be reduced by half, because 8 times 7 is always equal to 7 times 8. And for solving algebraic equations, you always have to move the numbers to the other side of the equations, and that involves inversion or complement understanding. And finally, by understanding the relation to operand principle, it helps you to check the answers. Suppose when you are supposed to do an addition problem and you get an answer that is smaller than the original number, you know that something has gone wrong and you better check. And empirical findings also support the relation between arithmetic principle and math achievement. So for example, Craig and colleagues show that children's and adults' understanding of AP actually predict their math achievement beyond that of number fact knowledge and arithmetic strategy efficiency. And these relations actually hold across a wide age range from childhood to adulthood. Cheng and Nuns also show that children's understanding of commutativity and inversion actually predict their math achievement, even after the controlling for autoregressor effects. And Anderson also showed that children with math learning difficulties have poorer understanding of APs. So there are different measures for assessing APs, and I will talk about this in detail. But here I would like to point out that a lot of studies in this field, they are using different measures to assess different AP understanding. So this is a problem because it's less likely for us to compare the understanding of APs because of the methodological confounds. And the other research gap in this field is that we don't know much about the cognitive predictors of different AP understandings. So various cognitive predictors are suggested to be important for various AP understanding. For example, if you have to discover a certain arithmetic principle, you probably need to hold multiple number sentences in your mind so that you can compare them. And this requires working memory and processing speed. And because it involves comparison and identifying similarities, it also involves intelligence as well. And for inhibition, it's proposed to be specifically related to the discovery of inversion. So for example, in inversion problem like this, A plus B minus B equals something. So the usual way of doing this is do the computation, you A plus B, and then you take away B, and then you get the answer. So in order to discover the inversion principle, you need to have a moment like, okay, something is strange, I better stop calculating and see what's happening here. So this requires the ability to inhibit your impulse to calculate. So that's why inhibition is suggested to be related to inversion. And for spatial skill, is also proposed to be related to the discovery of inversion or complement principle, because for complement problem like this, 4 plus 3 equals 7 and 7 minus 3 equals 4, it's just like mentally rotating the whole number sentence. So this requires some kind of spatial skills. And finally, numerical magnitude is suggested to be related to relation to operand principle, because this principle is about the relative magnitude of numbers. So having good sense of number may help you to actually discover the relation between the numbers in a number sentence. So the goal of this study is to identify the cognitive predictors of children's AP understanding, and we are using multifaceted assessment to achieve this goal, so that each principle we use 3 different measures to assess it. So we have 273 fourth graders here. So the mean age is about 10, and we have more boys than girls. So let me spend a little bit more time on the three measures that I'm using. So the first one is evaluation of examples. So in this task, children are shown the work of two hypothetical students, P and Q. Each of them solved 3 problems. Okay, both of them got the first problem correct, and each of them got one of the remaining problem correct. Okay, so the children's task is to decide which hypothetical student actually use more efficient ways to solve math problems. So the trick is that the last 2 problems, one of them is actually relevant to the first problem. For example, here, I minus A is actually related to the first problem. They are complement problems. So for children who are aware of this complement principle, they should be able to see that, okay, I actually don't have to calculate this because the student already solved this. So I can use this problem to help us with the second problem. So as long as children are aware of this, they will be able to see that student P is the one who are able to use more efficient ways to solve problems. So the next task is explicit recognition. So we convert the arithmetic principle into a statement like this. If A plus B equals C, then is C minus B equals A. So their task is simply to decide whether these statements are correct. And they are given time limits so that they can't substitute numbers to get the answer, to check the answers. And finally, we have the most common measure in this field, the application of procedures. So in this task, each time students are shown 2 problems. One is the reference problem, which is solved already, and they have to solve the target problem. So the trick here is that some of the target problems are actually relevant to the reference problem. For example, here the target problem is actually the complement problem of the reference problem. So that if children are aware of this principle, they will be able to solve the target problem without doing the calculation. Okay, but for other problems, so the 2 are actually not related, so they will have to resort to calculation. But we purposefully impose a time limit so that they actually won't have enough time to solve those control problems. So for predictor measures, we have ravens for intelligence, backward syllable span and backward causal span for working memory, cross-out for processing speed, stroke for inhibition, mental rotation for spatial skills, and number line for numerical magnitude representation. So these are the results. As you can see here, we have a total of 9 AP measures, and the participants seems to do pretty much well. The performance is all about chance. Next, we check whether the 9 different tasks can be grouped according to the 3 arithmetic principle factors. And the CFA suggests that the model fits the data very well, and we are able to create a latent variable for each of the arithmetic principle measures. And finally, we have run a structural equation model to see how the cognitive predictors actually predict the 3 arithmetic principles. So here we see that there are some cognitive factors that are important for AP in general. For example, we have fluid intelligence, verbal working memory predicting all the 3 APs, and processing speed predict both commutativity and relation to operands. Next, we see that this visual spatial tasks, for example, visual spatial working memory and spatial skills, both predict inversion. Finally, we see that for relation to operands is predicted by inhibition skills and numerical magnitude representation. Okay, so we see that some cognitive variables are important for general AP understanding, while some role is more specific. So this is the summary of the results. We can see above chance performance in all the 3 APs. So it seems that 4th graders, by this time, they have reasonable mastery of the APs. And we are also able to use multiple measures to assess arithmetic principle understanding. And we are able to create latent variables to measure this AP understanding. And I think this is important because unlike some of the previous studies which use different measures for different APs, so they aren't really comparable. But if we use consistent measures for different APs, we are able to compare the results more easily. And finally, we see different prediction patterns here. For example, we see that IQ, working memory, and processing speed seems to be important for general AP understanding. Spatial skills is important for inversion understanding, and numerical magnitude is important for relation to operand understanding. So the string part here is that originally we proposed that inhibition should predict inversion understanding, but in fact, it's actually predict relation to operands. So we do not have a clear reason why that is the case, and we welcome suggestions. So I think that the important implication of this study is that first is an example of using multifaceted assessment to assess children's AP understanding, so which help us to get away with the methodological confounds. Second, we see differential prediction patterns of AP understanding. And I think this can be important as well because, for example, we see that spatial skill seems to be important for inversion understanding. Maybe in future studies, when we design intervention to improve children's inversion understanding, maybe we can make use of the spatial elements to a greater extent, or maybe we can try to train children's spatial skills and see whether this helps them to acquire the inversion or complement principle. So I hope that this study would provide more ideas for researchers in the field to develop further studies in this area. So that's all for my presentation. I have to thank the Research Grants Council in Hong Kong for supporting this research. And I have to thank my graduate student and my research interns who have devoted a lot of time to collect data. Okay, so if you have any question about this study, please email me. So thank you very much. Okay, so are there any questions? I think we can have one.
I do have a question, if I may. Thank you. That was a very interesting talk. I'm curious about whether you've thought about the possibility that these different principles are the subject of explicit instruction to different degrees, and whether that might explain the different predictors. For instance, I don't know about the educational system in Hong Kong, but my kids are about the same age, that these principles are taught, and commutativity is taught very explicitly. Relation to operands, probably not at all, and inversion is probably somewhere in between. So I wonder if those kinds of differences might have anything to do with which predictors relate to which of these outcomes.
Well, this is a very interesting suggestion, and I think that instruction will certainly affect the results in some way. But I actually did look into the curriculum in Hong Kong, and I found that commutativity was indeed mentioned, but it was only briefly mentioned, like one half of the page in the textbook. And inversion and relation to operand principle is basically not covered in the curriculum. Okay, so maybe how the principle is taught may affect commutativity understanding, but I guess the effect is not that strong for the other two principles. So Adam has a question as well, right?
Yeah, so coming out from the other standpoint, I'm just curious. No, not. Don't know if you. Adam's AirPods. It turned off my microphone, so apparently people can hear me now, I think. Okay, good. Before it was the wrong one. Sorry, I should know tech. Anyway, so coming out from the other side, I'm just curious about this. I find it really interesting. To what extent do you think the problem format is responsible for what is actually what's being activated and what particular capacities are being engaged? So with the SCAD star model, the 3-term problem was originally proposed with that format. And within that model, we've seen in previous research a relationship between inhibitory ability and inversion shortcut use. We've seen that for children who use the inversion shortcut, the product of multiplication operation isn't active in memory, but for children who use left or right, there is presence. For children who use negation, the product of multiplication is less activated, so the idea that it's been somewhat inhibited. So we've seen some evidence, but it's in that 3-term problem format. Now here, say for example, with inversion, you've got this different format. So are we investigating the role of these different capacities in the application of these concepts, or just these specific problem, like representations, like the way they're shown on the screen, the way the problem format? There's been some discussion on that. I'm very curious.
Yeah, I'm not sure whether I got it completely from you. So you're talking about like the problem format, the 3-term versus 2-term problem, and whether we are talking about like the acquisition of the principle or the application of the principle.
The application of the principle, say for example, so here you found a lack of a relationship between children's performance on an inhibition task and then their performance on these inversion problems. And these inversion problems are of a different format than what has been used previously. So how much is it the way the problems are represented as opposed to the inversion concept? And like, is it that inhibition is not involved with inversion reasoning, or is it just this problem format? But that's what I'm always been curious with.
Now, that's a very interesting question. So in this study, because we only use 2-term problems, so we can't actually tell whether, like how the problem is presented and how the cognitive correlates actually predict the principal knowledge. And in future study, I guess maybe we can put this into an empirical question and test, like whether 2-term problem actually requires something different from 3-term problem. But here we are using 2-term problem because we want to be consistent across multiple principles. Because for relation to operand principle, basically we don't have 3 terms problem. So that we are afraid we create some kind of difficulty in comparing across multiple principles. Okay, thank you. And now maybe we can pass the time to Richard.
Okay. All right, thanks everyone for coming. So I'm going to talk a little bit about a study we've done on spontaneous attention to relations and whether or not they may kind of predict or be associated with arithmetic principle knowledge, including both with positive numbers and with negative numbers. So first, I'd like to quickly acknowledge the team that been working with me on this and other projects. Graduate student Josh, Cameron, our research assistant, and our new postdoc Lauren. So I'm sure with this group, I guess I don't need to go over too much of a definition of arithmetic principles. We kind of think of these as kind of rules and regularities within problem domains, especially in mathematics. What I'm mostly going to be focusing on here is relation to operands. And what I'm interested in is the kind of difference between how this works out when all the numbers involved are positive, so like an A plus B equals C situation where A, B, and C are all positive, versus the inclusion of a negative number. And in this study and in the work that I've done, we usually just stick to one negative number in the equation. So it'll be something like A minus negative B equals C. And the participants will have to think about what the kind of relative magnitude of the numbers involved may or may not be. So in this study, we're primarily focused on subtraction because based on prior work that we've done and others have done, people are a little bit better at addition in terms of understanding these principles, a little less so on subtraction. So we're looking at improving people's knowledge. We didn't want to start at ceiling. So we'll be looking at relation to operands for subtraction, either with only positive numbers or including a negative number, usually the second number in that equation. So, of course, folks here may know, arithmetic principle knowledge is kind of interesting and important for a variety of reasons. It tends to be associated with better performance on arithmetic tasks. It is sometimes associated with how participants approach doing arithmetic problems, such as word problems. Previous work shows that you can have kind of very different displays of knowledge of arithmetic principles in contexts that only include positive numbers versus contexts that include negative numbers. And previous work has also shown some association with kind of encoding of symbolic magnitude. So my prior work looked at whether or not children were attending to whether or not these symbols were kind of relatively large versus relatively small numbers, and how that was associated with their knowledge of relation to operands. So kind of related to that, recently there's been kind of a lot of work on spontaneous attention to number sometimes, and also spontaneous attention to relations. Kind of a very interesting literature in the last 5 to 10 years or so. What I've been really interested in is kind of spontaneous attention to relations. And we've started looking at that using a task first developed, I think, by Chan and Mizoko. We use our own kind of variation of it. It's essentially like a card matching task. So the idea here is there are these kind of abstract non-symbolic shapes, and the participant is asked to match one of the bottom 4 with the top middle. And you can kind of see there are a couple of different potential matches. So there's kind of more of a shape-based match with just a circle or just a triangle. There's also 2 other matches, so the ones on the ends that are kind of relation, right? And so there are a couple of ways to thinking about the relationship. So that the top match has 2 circles and 1 triangle. On one side, we have 4 circles and 2 triangles. You could think about that as the same relationship in terms of the ratio, right? On the other side, we have 3 circles and 2 triangles. You can think about that as similar in more kind of an additive way. There's 1 more circle than there is triangles. Now, I thought people would be much more interested in the first one, which we call the kind of multiplicative match, rather than the additive match. We actually did some work related to this with children that has just come out in developmental science, and children are completely uninterested in the multiplicative match. So that's the one on the far left. They are much more interested in a more kind of additive match. So in thinking about this kind of potential spontaneous attention to relations, I was really interested in whether or not this was going to be kind of similar to attending to relations when looking at a symbolic arithmetic problem. So my prior work has suggested that children who tend to think about relative relationships when looking at an arithmetic problem were more likely to kind of show knowledge of relation to operands principle. So maybe we could kind of take some of these principles about spontaneous attention to relations and see if there's any kind of connection between how people are doing on that task and how they're doing on the kind of symbolic arithmetic task, and whether or not improvement on spontaneous attention to relations or some sort of training or feedback might transfer to what they're doing in the symbolic realm. So, our basic question here is, does spontaneous attention to relations with that kind of non-symbolic card-based task predict principal knowledge with negative or positive numbers for relationship to operands? So our hypotheses can kind of be broken up into a couple of different groups. First is spontaneous attention to relation associated with relation to operands principal knowledge for positive numbers, or for including negative numbers. is feedback on the spontaneous attention to relation task going to actually change their scores on that task? So just staying with that kind of card task is giving them kind of feedback about what selection they should make actually going to change their behavior on that task. And if so, or kind of, given that they're getting that feedback on the spontaneous attention relations task, is that going to increase their relation to operands knowledge for positive numbers or for negative numbers? Now, we did a similar study to this with children, but in this particular study, we were working with adults. So we had 174 adults. This was run online, Amazon Mechanical Turk, which means that we did actually get a very good age range. So the participants are anywhere between 18 and 65, 70 maybe. And the average age is usually about in the mid-30s or so. And we broke them into 2 different groups. So there's 2 different kinds of feedback that they may get. The additive relation feedback. So those participants are told that the additive relation match is the better match for the spontaneous attention to relations task. And a shape match group, which is told that the shape match, just going from circle to circle, is the better match. So they went through 4 different tasks, which are really just kind of repeats of 2 tasks. So we got an initial measurement of their spontaneous attention to relations using that task, an initial measure of their knowledge of relation to operands. And we did that with a kind of basic ranking task. So we told them that 3 children had solved this really simple arithmetic equation, something along the lines of 12 minus 3 equals blank. You'd have 1 child who got it correct, so 12 minus 3 equals 9. And then you have 2 other children who got it incorrect. 1 would kind of violate the principle, so they would say 12 minus 3 equals some number larger than 12. So it might be 16 or something like that. And then you would have another, the 3rd one would get it incorrect but not violate the principle, so they might say 12 minus 3 is 5 or something like that. Now we did match those 2 incorrect answers to make sure they were the same distance from the correct answer. So on every single trial, they have 1 correct possibility, 2 that are incorrect. They're equal distant from the correct answer. 1 kind of violates principle and 1 does not. So the expectation here is that if you are attending to that principle, you tend to rank the person who violates the principle as understanding arithmetic the least. This is kind of similar to what we've used in prior studies. Sometimes we use rating, sometimes we use ranking, but it tends to work relatively well. After they've done that, they then do the spontaneous attention to relations task again. And in this case, we give them feedback. And by feedback, I basically mean we just kind of circle what the right answer is. We don't tell them what it is. It's kind of like a pared down version of the Wisconsin sorting task. We don't tell them what the rule is, but we tell them which answer is the correct one. They tend to respond to that pretty quickly. After doing that, we then have them do the relation to operands task again. Same basic idea, slightly different examples, but we have them kind of go over it again. So for the results, the first thing we took a look at is whether or not there is even an association to begin with between their performance on the spontaneous attention to relations task and how they were doing on the relation to operands, principal knowledge task. And we surprisingly really didn't find anything. We looked at this just using kind of a straightforward regression for those 2 cases. And you see the numbers in the paper, which should be coming out in a couple of months or so. We just didn't find any relationship between how they were doing on the spontaneous attention to relations task versus knowledge of arithmetic principles. Next, we just looked at whether or not their performance will actually change on the spontaneous attention to relations task. And we found that one actually, it changes very swiftly, right? So in the beginning, in the kind of pre-training phase, we kind of took a look. So on the vertical axis here is just kind of how often they're picking each particular option. Here, I'm just comparing picking the additive relation match versus either one of the two shape matches. Pre-training, they're about even. Post-training, for people who are shown feedback to now start picking the additive relation, they swiftly go to not quite at ceiling. Maybe kind of unclear why adults can't hit ceiling. That's pretty clear feedback, but we're running this online, who knows? But they do seem to be able to change their behavior on that task really quickly. So remember, if you kind of think of it almost like a Wisconsin card sort type of task, given a little bit of feedback, they can switch up what the kind of rule is inside their head pretty quickly. But if you then take a look at the change in how they're doing on relation to operands tasks, what we actually find is that there's no difference between the two groups. So some people had feedback that suggested that they start marking additive relationships. Some people had just the shape match. There's a big difference in how they do on the spontaneous attention relation task, but when you look at the relation to operands task, which is here, if you compare the blue and the red, it's the same every single time. So the relating of the non-violation is no different for the two different groups. And here we actually see a reduction in kind of how well they're showing their knowledge. So this is just for positive numbers. They do relatively well pre-training, so they're rating the violation examples as worse. They tend to rank those more close to third. But post-training, they're totally even. I'm not exactly sure what's going on there, but it's actually kind of the opposite, negative numbers. So prior to training with negative numbers, they were not doing really well. They were actually rating the violation equations as a little bit better than the non-violation equations. And then after training, both groups are doing really well and are noting that violations of relation to operands with negative numbers are significantly worse than non-violations. So the results are a little puzzling. We're not actually sure what's going on. Kind of the main thing we can tell is that people are moving around in terms of what their behavior is, and it seems like all the participants are kind of moving as a group, so to speak, but we don't know exactly what's going on. So the findings suggest that we've demonstrated that feedback can lead to changes on the spontaneous attention to relation task. So they're absolutely able to make changes on that task. There doesn't seem to be any differences on the relation to operands principal knowledge task between the two groups. And it's unclear if the kind of training or feedback that we gave them on the spontaneous attention to relation task can transfer to the arithmetic principle task. And it could be an issue of it going from non-symbolic to symbolic. The prior work that I talked about that seemed to work relatively well with children, that was all symbolic format. So it could be this case that we're just not going to have them jump from one format to another one. So we can see that adults can adjust their attention with kind of minimal feedback on that spontaneous attention task. Children that we tested weren't necessarily moving nearly as easily. But there seems to be no clear effect of spontaneous attention to relations on their knowledge of relation to operands. And so it could be due to a lack of transfer across formats. And the prior work that we've done looking at this was really just on one format. So that could be kind of the potential issue there. And with that, I think I will end. Please let me know if you have any questions.
So as time is running out, so maybe we can pass the time to Anna, our last presenter.
So thank you.
I will just share my screen. Get that ready. All right. Okay. So hi everyone, my name is Anna Bartel, and today I'll be discussing whether tape diagrams focus on conceptual principles. I'd like to briefly acknowledge my long list of co-authors there on the right-hand side. What I'm presenting today is just a very small piece of a much larger project that's being conducted at my home university, University of Wisconsin, along with our collaborators at Carnegie Mellon. Suppose I were to ask you to solve this equation, 2x minus 8 equals 0. The first step you might complete is to add 8. And if I were to ask you what you did, well, you'd say, I added 8. Then if I asked you what to do next, you'd divide by 2, which leads to you getting the answer. But there's another question I can ask you about your reasoning. And this is why you chose those specific equation solving steps. So if I ask you why you added 8, you might say because addition is the inverse of subtraction, and you divided 2 to do the same thing to both sides to keep the equation equal. And in order to get the answer, you had to isolate the variable. The what and the why in equation solving have specific names. The what's called procedural knowledge, which is understanding the series of steps to solve a problem. And the why is called conceptual knowledge, which is understanding the reasoning behind a series of steps. Today, we're going to be focusing on promoting specific conceptual principles in equation solving. The conceptual principles we're focusing on today are doing the same thing to both sides, inverse operations, equality, and isolating the variable. Now I'll give you some specific examples of what these conceptual principles look like in the real world. The following quotes are from 4 middle school students in the study that I'll be talking about today. When one student evoked the principle of doing the same thing to both sides during equation solving, they stated, what I did to each side of the equation was I added 8, because on both sides of the equation, you have to have the same thing done to them. When a student evoked inverse operations, they said, I added 8 to the negative 8 in the problem so they cancel each other out. Regarding equality, a student said, I did addition to keep the equation equal. And finally, for isolating the variable, one student said, to get x by itself, you have to divide this by 2. However, students don't often provide conceptual explanations and rather provide procedural explanations during equation solving. This isn't ideal because conceptual knowledge has demonstrated benefits to procedural proficiency, flexibility, and efficacy in problem solving. Therefore, we were interested in what sort of instructional techniques support conceptual understanding in algebra. The 3 instructional techniques we'll focus on today are worked examples, self-explanations, and tape diagrams. Worked examples are written examples of a solution to a problem. Self-explanation is when learners generate explanations themselves, and self-explanations don't necessarily have to be verbal, as I've visualized in this icon, but in this presentation, we'll be detailing verbal self-explanations. I don't know if I'll have time for a Q&A, but I do have a supplemental slide that details some work hot off the press that my collaborator and co-author, Tomo Nagashima, is leading in regards to diagrammatic self-explanations. So if anybody's interested in that, we can talk about it. And finally, tape diagrams are a specific type of visual representation where quantities are depicted as horizontal bars. So if we put all this together, I can sort of put together this huge research question that asks, does self-explanation of worked examples with and without tape diagrams promote a focus on conceptual principles? We answered this question by recruiting 41 middle school students, and we randomly assigned these students into a control condition and experimental. I know you might be thinking our sample size is small, and you're right. And as a result of that, I will, for the most part, be describing trends in the results and some descriptive results. For transparency's sake as well, this was a large study with many variables, which you'll see when I detail the procedure in the following slide. So while there's more going on in this study that I'm going to discuss today, it's accurate for us to think of the control condition as a group who didn't receive tape diagrams and the experimental condition as a group who did receive tape diagrams. So now into the procedure. Participants were first administered a 7-item conceptual knowledge pretest, which included items of all the conceptual principles we discussed earlier, and they are adapted from these references down here. Next, participants solved a 1-item equation solving pretest. After the pretest, students solved linear equations through an intelligent tutoring system that we called the NET. As you can see in these small icons, equations in the experimental condition were paired with corresponding tape diagrams, while there were no diagrams in the control tutor. So I'm not going to talk about Lynette today and the results, except for some future directions or in my supplemental materials. And that's because the study I'm talking about today, it was originally designed to enhance a new version of self-explanations in our intelligent tutoring system, Lynette, which I will talk about in future directions. Next, participants were asked to explain the set of steps completed in worked examples, and you'll see an example video of this later on. But for each step in the solved equation, participants were asked what the student who solved the equation did and why they chose to do any particular step. We coded students' explanations during the worked examples for the conceptual principles mentioned earlier. Students then solved the one-item equation solving post-test and an isomorphic conceptual knowledge post-test. The entire procedure was about an hour. Given the first question I posed to you is pretty big, we decided to break it up into smaller pieces throughout this presentation. So the first is, do students in the experimental condition perform better on conceptual post-tests than students in the control condition? Before I show you the results, I'll orient you to the graph. On the y-axis is conceptual knowledge post-test score. And while the y-axis has a maximum score of 6, the assessment was out of 7 items. On the x-axis, we have our conditions, and the graph is plotting estimated marginal means because we're controlling for conceptual knowledge pretest. Overall, we find that condition is not associated with post-test performance. However, you can see that there's a lot of variability in these scores. Additionally, we noticed a lot of variability in how students were explaining worked examples. So this led us to wonder, if condition isn't associated with post-test performance, does evoking principles during worked examples relate to post-test scores? So we wanted to step back and refocus. We decided to look more fine-grained at how students were interacting with the worked examples across conditions overall. So let's just watch an example in the experimental condition of a participant explaining a couple steps in this worked example.
4x plus 7 equals 19. And this is showing that 4x and 7 are the same length as 19. Okay. How did the student get from step 1 to step 2? They took away 7 from both sides. So they took away the 7 and they took away a 7 from the 19. So you can see that here, and then they took away the 7, so it was 4x equals 12. Same thing. And why did the student choose to do this? So that they could get rid of the 7 and just have the variable and just have that number, so that they could easier just solve it where it's just like x equals the number.
Again, for each participant, we coded the number of conceptual principle mentions and what specific principles they were mentioning. If you picked it up here, this participant mentioned isolating the variable there at the end. So this led us to the question, does the number of conceptual principles mentioned when explaining worked examples across conditions predict conceptual knowledge post-test scores? Again, we have conceptual knowledge post-test on the y-axis, but this time we have the number of conceptual principles mentioned on the worked examples on the x-axis. And this time around, we aren't looking at differences between condition, so we control for it here along with conceptual knowledge pretest. Overall, students who mentioned more principles when explaining the worked examples scored higher on the post-test. And if anybody's interested in learning more about this effect and its interaction with prior knowledge, they should head over to my co-author Nick Vest's poster at the Society for Research in Child Development, but I also have a supplemental slide about it. But next, we were interested in whether different types of worked examples led students to provide richer explanations. And I haven't told you this yet, but we provided students with 2 different types of worked examples. So we were interested to determine if one or the other led to students to provide richer explanations. So you already know that the first type of worked example we gave students was a correct worked example. Students were also given an incorrect worked example where there was one problem-solving error, and participants were asked to identify the error and why that error was incorrect. So here's a larger version of the correct worked examples for both condition, and here's the incorrect worked examples, and as you can see, that error is in step 2. So back to the question, we were interested in whether the number of conceptual principles mentioned when explaining correct or incorrect worked examples across condition predicted conceptual knowledge post-test score. Here we have the same x and y axis as before, but we have an additional predictor, whether the worked example was correct or incorrect. Originally, the worked examples are within subject, and I intended to test this interaction through a linear mixed effects model, but the model was not having my sample size, so I just tested the slopes individually for each line. Again, controlling for pretest and condition. Overall, there's not a significant effect. However, descriptively, the trend suggests that mentioning more conceptual principles while explaining incorrect worked examples may be related to higher conceptual knowledge at post-test. So next, we wanted to bring tape diagrams back into the equation and investigate whether the presence of tape diagrams influence the number of conceptual principles mentioned. Here, for the first time, our y-axis is different. Note that now our y-axis is the number of principles mentioned. On the x-axis, we have worked example type, and up here in the legend, we have our condition. For correct worked examples, we found no difference between conditions for mentions of conceptual principles, but for the incorrect worked example, we found the experimental condition mentioned more conceptual principles. Given this difference in overall construct mentions, we were interested in looking at this same sort of trend with our specific conceptual principles. As a reminder, the specific conceptual principles we'll be detailing are doing the same thing to both sides, inverse operations, equality, and isolating the variable. Here on the y-axis, we have the probability that a participant mentioned each of the 4 conceptual principles. The dependent variable is binomial, so we ran a generalized linear model. On the x-axis, we have whether the worked example is correct or incorrect, and in the legend again is our condition. For the correct worked example, there was no difference in the probability of mentions for most of the conceptual principles, and descriptively, students had a higher probability of mentioning equality in the experimental condition. For the incorrect worked examples, students in the experimental condition had a higher probability of mentioning conceptual principles, and this was a significant effect for inverse operations and trending for everything except equality here. What this means is that having diagrams on the incorrect worked examples increased the probability that students used richer explanations. And this isn't on the slide anywhere, but students who were in the experimental condition for both correct and incorrect worked examples tended to produce 2 or more principles, while students in the control condition tended to produce 1 or less. And I do have a graph about this in my supplemental slides if anybody wants to talk about it. But in conclusion, different types of worked examples elicited different rates of principal mentions. Specifically, incorrect worked examples with tape diagrams elicited the most. And mentioning conceptual principles on the worked examples was associated with post-test performance. And this poses some interesting questions for instructional design. So how can we continue to encourage students to express conceptual ideas? You may have noticed in some of my graphs that it's not like students were mentioning like 6 principles. They were mentioning very few, but when they do say them, they're helpful. So how can we design future worked examples to scaffold more conceptual explanations? Well, one way we're trying to encourage students to say more in the equation solving process is by combining worked examples, tape diagrams, and then probing them further if they didn't provide a conceptual response. Here, we have a similar tutor that was used in this study, but this time they're not only problem solving, but also explaining worked examples with our what and our why questions. So here's just a very brief clip for you to see it in action. So this is not a verbal self-explanation anymore, but that was just an example of a student clicking through the tutor. And it wasn't really a student, that was our project manager, Elena. But as you can see, students are shown the first 2 steps of an already solved problem and asked to report what steps the student who solved the problem did and why they did it. So in that clip, the student answered the why question correctly. Here you can see all the options that students can choose from, and you may notice that there are more than one correct why answer. And students can select whatever they want in that regard. But you might also notice that we provide answers that are correct, but don't explain why the step was correct. For example, if a student were to select that this step was correct because the step gets rid of the 3, the tutor would provide feedback to that student that, well, yes, that's true. It doesn't explain why. And we're currently testing the effects of this tutor in a study that is ongoing, like at this moment. And we hope to report back some interesting findings soon. I'd like to thank all of my co-authors from UW and Carnegie Mellon, my research assistants who work harder than lots of people, and all the members of the Cognitive Development and Communication Lab, and of course our funders at NSF and the US Department of Education. Happy to take questions if there's time. We'll also accept any follow requests, but yeah. And maybe I should leave my slides up because I reference supplemental slides so much, but I don't have to. So any thoughts on stopping to share or continuing to share?
I don't have any, but I do have a question, if I may. Thank you. That was a very interesting presentation. I noticed that in the categories of explanations, you have, I think, explanations that seem to me like they're qualitatively different categories. That is, there are some that are explaining why a step is mathematically legitimate, why it's allowed. And there are others that are stating why in terms of the goal, what it achieves. And I'm curious whether you consider those to be the same sort of conceptual knowledge and why you consider the second type, explaining in terms of the goal, to be a type of conceptual knowledge at all. I could see an argument for saying that explaining the goal of a step is really part of your procedural rather than conceptual knowledge. So can you speak to that?
So are you referencing in here where it's like a correct, it's like a valid but not necessarily a helpful step?
No, I was thinking if you could go back maybe one or two more slides. Yes, this page. So for example, doing the same thing to both sides is an explanation of why a step is legitimate. It's always legit to do the same thing to both sides. It doesn't necessarily get you anywhere in terms of solving the problem, but it's always legit. Isolating the variable is your goal. If you can successfully isolate the variable, you've solved the problem, but not every step that you could do to isolate the variable is mathematically legitimate. So those seem to me like two different sorts of explanations. One says why it's allowed, the other says why it's productive, if that distinction makes sense.
Yeah, I mean, it does, and I don't have an answer for you. I'm sure we've discussed this somewhere, but, and there were discrepancies in how often students, I mean, even said these things. And so it's possible that at different points in time, like in those steps that they're explaining the worked example, that some principles are evoked more than others. And I think that that would be interesting to look at that step by step to sort of maybe answer your question a little bit more, or at least to figure out when the differences in those principles could be evoked in the equation solving process.
Thank you.
Thanks.
So
This is Anna. This is Renee Grimes. So, were you a part of Adam Sales' data mining roundtable this summer? Did you talk about the some of this data?
No, I was not there. No.
Okay. I just thought that this sounded very familiar to one of those. So, how large of the? I know that you said this was part of a larger study. So, how large is your, or are you doing any data mining on this now? Looking at, let me see what my question wants to be. I don't have this well articulated. Let me think a minute how I want to ask this and I'll get back to you.
Yeah, well, they're like, this isn't like a piece of, I mean, maybe I didn't say that correctly, but there's a bunch of ongoing projects that are all related to this. And this was just meant to be like almost a pilot study for the study that we're conducting right now. And we ran the study to try to see exactly what types of explanations students were giving when they were solving worked examples for the explicit purpose of like including them in our future tutor. And so we have, Tomo actually has a different type of tutor where it's a diagrammatic self-explanation. So we have different types of tutors. Yeah, so it's not like one large project, but like a bunch of smaller projects that are all semi-related.
Okay, great. Because I think I was really kind of getting at what David was asking too about those nuanced differences in those questions. Well, they're not actually nuanced, but
right. Yeah, haven't done anything like that yet.
Okay, so we are like 11 minutes out of the time. So thank you all the presenters for the presentation, and thank you for all the attendants' attention. So I really hope that this symposium will stimulate a lot more studies on this area, on principled knowledge, because this is important. Okay, so thank you very much. So I will pass the time back to MCLS.
Thank you for attending, everyone. Good night or good morning, depending on where you are, or maybe even good afternoon. We'll be hosting soon a session of like speed network for people that are trying to find more participants for proposing symposium for next year MCLS. So we'll be advertising that. Just keep an eye on that. Thank you. Thank you all the presenters. This was very nice.
Thank you.